we're going to get started right away because we have an exam to prepare for. Okay, so I'm going to basically look at the practice exam and maybe offer you some advice, or at the same time you can ask me questions, just in case you wonder, exactly what's going to be on the exam and so on and so forth, because we didn't make a decision until this Monday, this past Monday, just a few days ago, to basically not have a lot of the questions on Lewis structures. I mean, I expect you to have an idea what are Lewis structures and be able to tell me, or to answer questions, basically, to answer questions based on some given Lewis structures. But I don't expect you to be able to draw them, okay? Even though by the time of the final exam, I'll have more expectations on that. Okay, so if I give you a formula, I mean, remember, at the beginning of the semester, I was just giving you formulas. Let's say, I don't know, NH3. Right, that's at the beginning of the semester. I give you a formula, and all you need to do is to give me a name. Okay, like this is, you can call this nitrogen trihydride, but more commonly it's known as ammonia. So that's all I ask. And then, gradually you start developing a sense of what this compound looks like. Okay, so maybe you would call this a covalent compound. Okay, we would call this a covalent compound, and then basically, figure out like at room temperature, for example, room temperature and pressure. Okay, what it looks like. Okay, which is basically a gas, a colorless gas. At room temperature, okay? And then we get into things like the structure, right? So you have the nitrogen forming a single bond with each of the hydrogens while keeping a lone pair of the nitrogen. Okay, so what I'm saying is everything is still expected on this exam. So knowing names and formulas, that's very minimum. And then perhaps knowing that this is a covalent compound will indicate to you that I don't know. Okay, that is unlike the ionic compounds, right? Ionic compounds would be things like sodium chloride and or sodium nitrate, okay? And so there are certain properties that are common to all the ionic compounds. And certainly this is not one of them. This is not ionic, this is covalent. So you would have to apply your understanding of the chemistry of the covalent compounds and be able to describe it. This is actually an inorganic compound, even though I'm not going to test you on this, but I did, try to make it clear at the beginning of the semester that there are certain compounds that are organic, and this one is not one of them, because first of all, there's no carbon, and even if there is, okay, CH3 is not necessarily a compound. CH4 is the smallest possible organic compound, CH4, has one carbon surrounded by 4 hydrogen, right? And this one is actually organic, even though it does not look like it. Okay, whereas CO2 is actually inorganic. But I did, try to make a brief distinction. I mean, a brief discussion of the distinction between organic and inorganic compounds. So this one is inorganic, it's covalent, so that immediately tells you a whole lot about this compound. Okay? So what I'm saying is on this exam, Okay, I don't expect you to be able to go from here to here. Okay, so even though I'll tell you, okay, consider this molecule, ammonia, NH3. And the next step, I'm going to provide this structure to you. I'm going to show you, okay, this is a possible structure for NH3. And I may not even show it to you like this. Maybe I'll give it to you like this. Okay, is there a difference between the structure on the left and the structure on the right? No, absolutely not. Okay, all this is showing in the Lewis structure is the connectivity between different atoms or different elements. So all I know is that, okay, this hydrogen right here is not connected with any of the other two hydrogen. Okay, they're not bonded together. But all three hydrogen are bonded to the nitrogen, which serves in this case as the central atom. Okay, so this kind of information I can get from this one or from this one and make no difference. Okay, so actually some students would wonder, if these two are totally different structures. Well, at this point, I can tell you in a definitive manner that they are identical structures. They're just being drawn differently. Okay, so again, at this point, all you need to do is to focus on the connectivity. As well as the features, like, okay, tell me what kind of bond is between nitrogen and hydrogen in ammonia. Is it a single bond, double bond, or triple bond? Okay, single bond, right? Okay, if you know that, that's good. How many lone pair are there on the nitrogen atom in the NH3 molecule?
One.
Just one lone pair, okay? This is called a lone pair. So it doesn't matter if you look at this diagram or this diagram, they tell you the same information, right? That there are two electrons, okay, that are not bonded with anything, okay? And those two electrons belong to nitrogen, okay? Why is that? Well, that's the way we draw Lewis structures, okay? That's the way that Lewis developed this model, okay? Which is very powerful, I mean, there's probably chemistry related to everything in the molecule. Like, this NH bond has something to do with the property of the molecule. And, obviously, there are three of them, and the lone pair here sometimes can be thought of as why NH3 is a base, right? Remember acid and base. Okay, the lone pair on the nitrogen is being identified as the reason why NH3 is a base, but sometimes we don't look at the lone pair at all. This lone pair here does not give us anything some of the time, but if you look at it from a certain angle, then this lone pair becomes a very important part of the molecule because it explains why this is a base. So all you need to do right now is, just accept these structures as given, and I wouldn't trick you like giving you a structure and ask you to point out what's wrong with the structure, because I don't think at this point it is fair. Okay, so I'll just give you, structures that you can assume to be the correct ones for different molecules, and then just answer a few questions about these structures. And like I said, we didn't make this decision until this past Monday. We just decided because we were running out of time, so there was no time for me to give you a proper review of the Lewis structure. So this is what we decided on doing, okay? And we never got to the valence bond theory. I mentioned it once in class, but it was never discussed. So you can pretty much just ignore the discussion of the valence bond theory, which is, I think, in chapter 10 of your book.
Is that the Vesper theory?
No, this is not the same as the Vesper. Or maybe this is not in chapter 10. Let me see. Yeah, it's actually in chapter 11. So we never touched the valence bond theory, which is in chapter 11. The VSEPR is different. VSEPR. We actually talked about this one Okay, the valence shell electron pair repulsion theory. This is totally different. These two, okay, are totally different theories. This one we did actually talk about, but only on the very last day. And I just basically ask you to know what it is and know what it does. Okay, this theory right here, which, okay, if you take it literally, it just says that valence shell electron pair. Okay, so that describes what? To describe these electrons that actually got, you know, that are actually shown in various Lewis structures. Because imagine, right, nitrogen has actually what, 7 electrons? Nitrogen, right, a neutral nitrogen atom would have 7 electrons. We go with 7 protons. So how come we're showing only 5 of them? How come we're only showing 5 nitrogen electrons instead of all 7? Okay, at this point you should be able to answer this question. Why am I showing only 5 in the Lewis structure?
There are 8 shown in the structure, aren't there?
Huh? This one, like in NH3, there are only 5 electrons from nitrogen. Where each hydrogen has 1 electron, you know that. Hydrogen has 1 electron and 1 proton. So I'm seeing the hydrogen electrons, all of them being shown. But nitrogen has 7. How come I'm only seeing 5 of them in the Lewis structure? Yeah, because, yeah, go ahead.
They're not out of balance?
Yeah. Okay, so if you look at nitrogen, right, it's 1s2, 2s2, 2p3. Okay, so explicitly, right, this guy Lewis is basically saying explicitly, okay, these core electrons of nitrogen, these are core electrons, C-O-R-E, core. These core electrons of nitrogen will not participate in any sort of bonding. Okay? Only the valence, the valence electrons. These ones, 5 of them for nitrogen. Okay? Only these outer shell or so-called valence electrons will participate in bonding. So there's no need to show all 7 of the nitrogen electrons. 5 of them, okay, these 5 of them on the valence shell, those are the ones that we care about the most, okay? And therefore, this, VSEPR theory basically is saying, okay, valence shell electron pair. So, there are pairs of electrons on the valence shell of nitrogen, okay? And I asked very specifically, what is this R here? Represent? Repulsion, right? R stands for repulsion, okay? So I guess this is the key word of the VSEPR theory. The valence bond theory has nothing to do with this whatever repulsion. Okay, the valence bond theory is completely different. Okay, so just remember VSEPR, the R stands for repulsion, and the VSEP simply refers to all these electron pairs that we end up putting into the Lewis structure to describe the molecule. So the repulsion refers to these electrons wanting to, be separated in space so that the maximum space is given to each electron pair. So obviously you don't want to put them like, if you're on NH3, you don't want to do this. You don't want to, just put all 3 of the hydrogens like this and then put the lone pair somewhere nearby. Okay, this is not a good situation for the molecule. And in fact, none of the ammonia molecule is found like this. Okay? But instead, experimentally, if you actually measure, you've done the computational experiment already. So you know that, mathematically, how do we maximize the separation, okay, for these 4 electron pairs on the nitrogen? Well, the maximum separation is achieved when you build the tetrahedron. Okay, so this is some kind of a 3-dimensional thing. Okay, where you have the 3 hydrogens, occupying the 3 vertices of the triangle base. Okay, And then basically you look in the middle of this triangle, and you look up, okay? And you're going to see the nitrogen right in the middle of the pyramid, okay, of the tetrahedron. And then the lone pair is going to be found, somewhere on top of the nitrogen. Okay, so I mean, if you actually compute the proper geometry, this is likely what you're going to get, from a computational program. But I guess you can also do measurements directly on ammonia molecules. If you have available a bunch of ammonia molecules, I guess you can do some kind of a direct experiment. Okay, but I guess you wouldn't be able to actually take a ruler or protractor, that's what they're called, and start to measure these angles, like you're looking at a model of ammonia. And the real ammonia molecules, they are too small to be measured directly. Okay, so the only thing you can do is to perform spectroscopy, which was why you were taught spectroscopy in the lab, because that's about the only thing you can do with molecules that are too small to be observed. Okay, the only thing you can do is to excite these molecules with photons. Okay, various kinds of photons will bring about different kinds of excitations, and it's through recording these sort of behaviors, like you try to use light to bring about some sort of excitation to the molecule. Okay, and then you can record these excitation patterns that are called spectra. Okay, what you get from here is basically the spectrum. Okay, the singular of that word is spectrum. So you get a spectrum, and basically by interpreting the spectrum, you get to know something about the molecule itself, like bond angles and bond lengths and bond strength and so on and so forth. Okay, but without spectroscopy, I mean, there's basically no way that you can do any direct measurement on the molecules. But I guess on a computer, you can apply the VSEPR theory and essentially mathematically calculate, okay, so I want to maximize the separation of 4 groups of electrons. We call these electron domains. Okay, because sometimes, it's not just one pair of electrons, so I wouldn't call them electron pairs, but these are electron domains, okay, that we want to have maximum separation. So that's essentially what the VSEPR theory, what it is and what it is being used for. Is to be used to predict molecular shapes. Okay, so this theory right here, it's for predicting, or the prediction of molecular shapes. Okay, so if I ask you what is the VSEPR theory and what is it being used for, then you can simply say so. You can say that VSEPR theory is the valence shell electron pair repulsion theory. And what is it being used for? It's for prediction of molecular shapes. Just keep things simple. Okay, this is precisely what the book tells you, and it's the same way that I'm going to tell you about the VSEPR theory, and that's the only thing I expect you to know from VSEPR on this upcoming exam. So I'm not going to give you this. Okay, I'm not going to give you a formula. Let's go back to the formula. I'm not going to give you NX3 and expect you to draw this and then expect a shape. Okay, so this is actually called trigonal pyramid. This shape right here is called trigonal pyramid. And I guess you're just beginning to learn about this. Right? I know you had 2 labs on this already, but I feel like, well, maybe we can, use a little more time. I can't spell pyramid. Yeah, that's good enough. Yeah. Okay. So Okay, so I wouldn't go from here, from the formula, and expect you to give me a structure. And also, I'm not going to expect you to go from a structure to a shape by applying the VSEPR theory. Okay, but I expect you to have an understanding of the way it goes, okay, from one to another. So if I ask you, okay, how do you go from Annex 3 to this structure over here? Okay, then you're going to say, well, you're going to basically use the octet rule to predict the Lewis structure. Okay, because that's the only rule that explains the whole structure here. Okay, and this is the only rule that this structure must obey. Okay, there are other things that goes into the construction of the Lewis structure. Okay, there are several other things that typically you have to watch out for, but primarily is the octet rule. Okay, if the octet rule is violated, then this whole structure shouldn't be accepted. But, since octet rule has not been violated by the structure, then we accept this structure as such. Okay, and then going from here to the shape, what are you going to say? What will explain the shape of this molecule based on the Lewis structure? Okay, what is the connection here from the shape to the structure? Well, I just said that. Yeah, it's that. Right. Yeah, VSEPR theory. So it's not a definition, but it's just an application of the VSEPR theory. Okay, to help us predict the shape of the molecule. Okay, so I just want to clear this up with you. Okay, so when you're reading or studying chapter 10 of the book, you know that there's a lot of discussion of everything. I mean, even with Lewis structures. Okay, even with Lewis structures, I mean, there are a lot of do's and don'ts, and a lot of details. Like, how do you begin with a structure? Okay, and how do you recognize single, double, triple bonds, and where to put the lone pairs, and so on and so forth. So that's all a lot of details that hopefully given an additional week or two before the final exam, you will be able to get a good grasp of all these additional details, and eventually be able to draw structures and predict shape on your own. Okay. All right. Let's do some problems. Okay, because I think that will be very useful at this point in time to have you solve a few problems. Okay, and last Friday and also in lecture, I basically showed you how to decide which bond, okay, is likely going to be formed between any two elements. Okay, so I hope you still remember how to do that. And if you need to see another example or two, I think we have time today to do that. Okay, but let's go back to the practice exam, which I have a copy of over here. Okay, and let's see.
Could we go over 5A?
Yeah, we'll get there eventually. Let me just see what I can say, for example, about question 3. So you want to look at 5A. Okay, we'll get there, but let's begin with 3. Okay, so imagine that you are taking an exam and you see this question on the exam. Okay, answer all of the following questions regarding ethanol and acetic acid. Okay, so part A of problem 3 asks you to answer this question. Should ethanol and acetic acid both be considered organic compounds? Why or why not? Okay, well, I guess this one you're not going to have to worry about. Okay, because I think I test you on this a little bit on the first exam, and I don't plan on testing you again on this one. So ethanol is given as C2H6O, and acetic acid is given to you as C2H4O2. All right, so part A again asks you whether they're both organic compounds, and my answer is yes, they're both organic, just because of the similarity in the formulas, but also, you know, they both contain 2 carbons, and you know, if you actually have a look at the Lewis structure, the Lewis structures of both compounds, you're going to see that they're constructed in a very similar way. So one of them has, you know, these hydrogens that are all over the place, okay? But the backbone, okay, the backbone of the molecule is fundamentally just carbon. So any molecule with a carbon backbone is organic. So this one is organic. This one right here, I mean, if you actually draw the structure, it's a little different. Okay, the hydrogens are not necessarily everywhere. Okay, they're here, but then you know you have 2 oxygens versus 1. So the structures of both of them are going to be different. You know, the more you start to look into the details. But fundamentally, again, this one has a carbon backbone, so is this. So they're both organic compounds. Okay, so that's part A, which you don't need to worry about. Part B is about the Lewis structures. Okay, construct the Lewis structures for both of these compounds. And like I said, you know, I'm not going to test you on the drawing of Lewis structures. So you don't have to worry about having to personally or individually construct these structures. But I'm going to, you know, provide the structures to you, and maybe ask you to answer a few questions. Okay, so I'm going to provide both of these structures to you. Okay, and then I'm going to ask you to answer some questions. Like one of the questions I might ask, which is kind of hidden in the statement of the question, is to identify the hydroxyl group in both of these structures. So I'm going to tell you, okay, both structure has something called the hydroxyl group. Okay, so it's a group of atoms. Okay, and I'll tell you, okay, the hydroxyl group is basically an oxygen bonded to a hydrogen, and then the oxygen is going to bond to something else. Okay, so what I'll ask you to do is to identify the hydroxyl group in either of the Lewis structures. I mean, both, actually, in both of these Lewis structures. Okay, so you would have to kind of circle the hydroxyl group in both structures. So if you begin with ethanol, where's the hydroxyl group?
Far right.
Yeah, I mean, it's just a basic matter of recognition. Okay, so obviously there's no oxygen anywhere over here. So the only oxygen you see in the structure is this one right here. Okay, and just check. Okay, this oxygen, is it connected to a hydrogen? Yes. Does it contain 2 lone pairs? Yes. Is it connected to something else? Yes. Okay, if your question is yes to all of these, then this is the correct part of the molecule, and it can be identified as the hydroxyl group. Okay, just circle it, and that would be okay. Now over here on this molecule, can you circle the hydroxyl group as well? Okay, now you have to be careful, right? Okay, there are two oxygens on this molecule. Okay, is this the hydroxyl group right here?
No.
C double bond with O, no. Okay, what about over here? C single bond with O. Still not, okay? Because what you need to do is to match exactly what I asked. The hydroxyl group has the oxygen and hydrogen. So you cannot just circle this and say, well, this is the hydroxyl group. This is not. Okay, this is a carbon single bond to an oxygen. Here, I want you to circle the oxygen bonded to hydrogen. So you have to redo this. You cannot just, circle anything and just pretend that, well, that's close enough. Well, I want something better. I want some, very accurate description of the specific part of the molecule that can be called the hydroxyl group. Okay, so you would probably have to do a better job than circling the C and O. So here, clearly you have oxygen connected to hydrogen. Okay, the oxygen has 2 lone pairs, and the oxygen is connected to something else. So this satisfies the requirement of being hydroxyl group. So I'm going to circle it. Okay, so that's how you do it. So you have this hydroxyl group here in this one, and likewise you have another hydroxyl group on the acetic acid. Okay. All right, and then probably there's not much more in part B, because originally I was asking for the structures, and now I'm going to ask you for recognition of the structure, of the various parts of the structure. Okay, in the 3C, I actually asked originally for you to draw resonance structures for the acetic acid molecule. Okay, this one right here. Okay, originally I asked for you to draw the resonance structure of this molecule. Okay? But I guess for now, since I'm not going to ask you to draw, I'll actually provide the resonance structure. Like this. Okay, I'll provide the resonance structure. And maybe what I'll do is to ask you to explain resonance. Okay, so clearly these two are resonance structures. At least that's what you have to assume, because I'm going to provide them to you and tell you that these are resonance structures. So can you explain resonance by looking at these structures and remembering what you've read or what you did in the lab, or what you learned in lecture as far as resonance is concerned. So what are you going to say?
For resonance,
Yeah.
they have the same chemical formula, but they different. That's not resonance now. But,
Okay, the same chemical formula, right? This is C2H4O2. This is also C2H4O2.
different structure, right?
Yeah, different structure, but in what way? Can you be more specific?
The
Well,
orientation of the atoms are different.
No, that's called conformational isomers. That's not resonance. It's not the arrangement of the atoms. Okay, the bond. Okay, and actually what I would suggest you to do is to just label these oxygens, 1 and 2. It makes it a lot easier. You know which one is which. So this is always oxygen number 1. Okay, and this one is always oxygen number 2. Now, is it a little easier for you to see what is resonance? So it's not, that atoms are being arranged differently, because that's the idea of isomerism, which is not resonance. Okay, isomerism means, that you have 2 different molecules with the same chemical formula, but just different connectivity between the atoms. Here, it's not, well, you might think, yeah, I mean, oxygen number 2 looked like it was originally connected to a carbon, connected to a hydrogen. Now it is doubly bonded to the carbon. So it's a very different structure, right? You might think like that. But the idea of resonance is quite different. It's not just a matter of oxygen number 2, you know, initially involving 2 single bonds, now it has a double bond. It's more than that, it's more. Okay, so you have to look at the other oxygen, which now has a switch, right? Because oxygen number 1 used to have a double bond, and now it's oxygen number 2. While here, oxygen number 2 used to have 2 single bonds, and now it becomes oxygen number 1. Okay, and this speaks clearly to this definition of resonance, is that 2 or more equivalent, E-Q-U-I-V-A-L-E-N-T, 2 or more equivalent structures must be used to represent a single molecule. This is called resonance. It takes a little time and experience to identify resonance. Okay, but you know, if you're going to take organic chemistry, okay, then this is absolutely required. You got to be able to see resonance structures. Okay, and you have to be accurate every single time. You cannot just guess or just pretend that you know it, but then every time you run into a resonance structure, you're not sure if it is really resonance. Okay? It is resonance because I need to draw both structures in order to represent just one molecule. I mean, both of these are acidic acids. Okay? I mean, with the chemical formula being the same, that's okay, but primarily, I'm concerned about these 2 structures. Okay, and I have to use both of them to represent the same one molecule, which is the acidic acid molecule, right here. Okay, so these are not 2 different molecules. They're both being used at the same time to represent one molecule, which is the acidic acid. Okay, so why do we need to use 2? To use 2 Lewis structures instead of 1? Well, that's because of here, oxygen number 1 and oxygen number 2. Okay? The idea is that these 2 oxygens, right, chemically, they should be the same. Which means that, you know, so let me just do one thing to show you. Okay? So let me just erase the hydrogen for now. I'm going to erase the hydrogen. And in fact, I'm going to make it H plus and H plus. Okay, so I'll just take away the hydrogen while leaving behind the electron from the hydrogen. So making another lone pair on this oxygen number 2 and make another lone pair on this oxygen number 1. Okay? What I'm going to do is I'm going to pretend that this hydrogen is going to come in. Okay? And try to basically form a bond with one of these oxygens. Okay? So this hydrogen is going to come in and try to form a bond with one of these oxygens. Okay? So the question is, should this hydrogen be bonded to oxygen number 1 or number 2? Why must it be 2?
Because it's less stable.
Okay, you might think so. Okay, you might think, well, this hydrogen comes in and automatically just take the correct oxygen and form a bond with that oxygen in order to form the original acidic acid structure that I had in front of you just a minute ago. Okay, experiment, however. Okay, I mean, what you're thinking is important, but it's also important to consider what is the, what is informed by experiments. Okay, experiment have informed us, that this hydrogen, right, when it comes in, it cannot distinguish between the two oxygen. Okay, it cannot. And so we wonder why, right? I mean, clearly, the way that we draw the Lewis structure, clearly there's a double bond here to this oxygen and only a single bond. Okay, then how come this hydrogen does not see them being different? Oxygen number 1 and number 2. Why is it not different? Because of the resonance structure. Okay, because there's no reason for oxygen number 1 to have the double bond, while oxygen number 2 has the single bond. I mean, I could just switch the bonds. Oxygen number 1 can have the single, 2 can have the double. Okay, there's absolutely no reason why one of these oxygens must have the double bond and the other one the single bond. Okay, and therefore we say that both of these are accepted, but you're using both to represent just one molecule. Okay, in this case we refer to as resonance. I mean, it's almost like the real structure. So let me try to draw another structure for you to consider. Okay, so you have CHH, C. Let's just put the two O like this. Put one O here, one O here. Okay, here's number 1, here's number 2. Why don't I just, make them look equivalent? Just put, one bond at least, right? One bond at least. Okay, but the second bond, I'm not going to be too concerned about where to put it. Whether to put it on oxygen number 1 or oxygen number 2. Okay, I'm just going to draw a dotted line to represent that, yeah, this is at least one bond, but the second bond is going to be shared equally by both oxygens. So experimentally, right, I refer to these experiments as the authority on this. Experimentally, this bond is about 1.5 bond. Okay, so it's not a single bond, but it's also not a double bond. And this bond right here, again, experimentally tells us that this is a 1.5 bond instead of definitely a single bond or definitely a double bond. So in this case, okay, you can draw this picture and call this the resonance hybrid. I like to think of it as the resonance hybrid because you are combining two things into one. Okay, so we call this a resonance hybrid. Okay, if you think of it this way, then clearly, when the hydrogen comes in and tries to form a bond, it doesn't matter which oxygen the hydrogen is going to, form a bond with. Okay, or if you don't like the resonance hybrid, then you have to draw both of these structures. Okay, and put the double-headed arrow in between in order to represent the same information as what is in this picture. Okay, so it's either 1 or 2. I mean, you have to draw both or draw it like a hybrid. And some people don't like the hybrid because these dotted lines sometimes are not clear, okay, what they mean. But here there's no question about, okay, which oxygen has the single bond and which one has the double bond. And the fact that you can draw the single bond on either of the oxygen tells you that resonance exists. And this is the definition of resonance. Okay? So I guess at this point, I mean, if you know what I'm talking about here, then I think you understand what is resonance. But yeah.
Can resonance only occur when there's a double bond and single bond involved?
Yeah, you can say that. Because if all the bonds are single bond, then there's no alternative. Like in the case of C2H6. So let me just erase isomerism, which is a very different idea. I'm glad you're looking into it already, but isomerism is a very different idea. So let me draw the C2H6 molecule. Okay? Is there any resonance structure to this one? The answer is no. Okay, because let's say I switch this hydrogen with this hydrogen. Or I don't mean to switch the hydrogen, but I mean switching the bond. I switch this one with this one. They are both single bonds. So what I had before is identical to what I have now. So this is not resonant. But in some situations, like you almost have to memorize some examples of resonance in order to have a good understanding of resonance. So the example that I would like you to think about, remember, is actually the nitrate Lewis structure. It's very powerful. If you understand what's going on here, okay, then I'm sure you understand what is resonance. But if you don't, then okay, maybe you haven't totally understood. So I'm going to draw the double-headed arrows like this. Okay, and this is actually there should be a minus charge on the structure. Okay, so I just put the minus in a circle like this, just to remind me that this overall structure has a -1 charge. Okay, but this constitute the resonance structures of nitrogen. Okay, so the hybrid is going to look something like this. You have the N, which has at least one bond with each oxygen, right? Okay, because every time you draw the Lewis structure, okay, the oxygen and nitrogen are connected. Okay, it's basically the nitrogen in the middle and it's surrounded by oxygen. Okay, every single time. So I have at least one bond between the N and any one of the O's. Okay, but can you tell me what this dotted line means? So I'm again going to represent the hybrid. This is the resonance hybrid of NO3 minus. This is the resonance hybrid of NO3 minus. Okay, so can you tell me what does that represent? This single line with the dots.
A single bond.
So it's more than a single bond. Otherwise, I would have drawn just a single bond. Right, okay, that's a good start. You don't know if this is a single or double bond, but if you have to put down a number, what are you going to put? 1.5, that's close. Okay, but I'll drop it by a little bit. I'll put 1.3. In fact, it's 3, 3, 3, 3, 3. It's 1 and 1/3, yeah, 1 and 1/3. Why? Because, well, again, if you put numbers on this oxygen, this is oxygen number 1, this is oxygen number 2, and this is oxygen number 3. I mean, there are compounds formed by nitrogen, right? Like sodium nitrate, something. Well, better yet, let me give you a better example. Let's say nitric acid, HNO3. Okay, nitric acid, which you've actually used in one of your earlier experiments. Okay, in a copper cycle experiment, I'm sure you have seen nitric acid. Okay, so basically nitric acid is the hydrogen plus and the nitrogen. Okay, somehow one is positive, the other is negative, so they attract each other. Okay, so they form some kind of a molecule. All right, so let's say the hydrogen is going to come in. Okay, and see the nitrate. Which oxygen is this hydrogen going to be bonded to?
There's a 1/3 probability of either one.
Yeah, I mean, it's all possible. Right? All 3 of the oxygens are possible. I mean, why would this hydrogen prefer one of these oxygens but not the other 2? I mean, if you look at just one of these structures, you might say, yeah, there's a double bond here. So you can break the double bond and kind of form that bridge to the hydrogen. like that. Okay, but don't forget, there are also two other possible and equivalent structures. Okay, essentially, you know, as far as the oxygens, there shouldn't be any single one of these bonds that is a double bond. Okay, the bonds between N and O. Okay, it doesn't matter which O. The bond is going to be about 1.3 bond. Okay, not a definite single bond and not a definite double bond. Okay, so you were all right. Okay, whatever you just said, okay, there's a couple of comments you made, they're all correct. Okay, except that I would revise this a little bit. It's not a 1.5 bond here. It's 1.3. Okay, because it's the average. Well, just look at oxygen number 1. Okay, 66% of the time it is a single bond. Okay, so 66% of the time it is a single bond. 33% of the time, you know, 1/3 of the time, it is a double bond. So I just kind of divide this by 3, and I get 1.3. So that's experimentally. Okay, if you do an experiment on nitrate, first of all, you're going to determine that none of the oxygen is actually having a double bond with a nitrogen, and also the fact that every bond is equal and it's approximately 1.3 bond. Okay, I mean, if you say 1.5, you know, I would accept it. I mean, at least it tells me that you're thinking in the right direction. You're thinking that this is, you know, can't possibly be a definite double bond, because if this oxygen gets double bond, then so should this oxygen, and so should this oxygen. So the fact is that none of them receive an extra bond. They're just going to share one bond among all 3 of them. So it becomes 1.3 bond in each NO bond. So it's a very, I don't know, you know, it seems straightforward. Okay, I'm sure you read the book, and the book is going to, you know, basically give you a very direct definition of resonance, maybe illustrate with a couple of examples. But in my experience, right, resonance is one of the most difficult concepts in chemistry for someone to understand, you know, from scratch, I guess. So, you know, if you know what I'm talking about here, then you know, I must congratulate you. You actually, you know, pretty, you know, have a pretty good understanding of chemistry. But if you're having trouble seeing what I'm trying to convey here, then at least write down this sentence. Okay, put it on your note sheet. You know, this time I don't provide any more notes, because I want you to go back into writing your own equation or note sheets. Okay, remember, each of you is allowed to bring in 2 sheets of paper. You know, single-sided 2 sheets of paper. So if I were you, I'm going to put this on one of the two pages.
Can we type those?
Oh yeah, totally, yeah. So if your handwriting is, you know, if you don't want to write, you know, using your own, if you don't want to look at your own handwriting, yeah, you can type. But I hope you're not going to, you know, just sell your note sheet to someone else. Because you had to type, okay, it's very easy for you to email it to someone else and, you know, sell it for a profit. I mean, when you get there, I mean, when you're professional, when you have your degrees, and, you know, you go to a bookstore, right? You can actually buy. You can buy these. What do we call those? You know, those laminated, 2-sided, you know, note pages or whatever, equation sheets, cheat sheets. Okay, so, you know, wait until you get there. Wait until you're qualified to, you know, create those sort of commercial products. And then, you know, if you ever get there, then, you know, I think you earn it. You know, you can sell your ideas as for profit. But at this point, you know, just prepare your own note sheets and use it for your own study, or use it for your own benefit. And, you know, you can work with someone else, but make sure you don't just prepare a note sheet and just photocopy it and let somebody else have it. Okay, this should be your own property, and you are the only person who will be allowed to use it. Again, if you have any trouble with the concept of resonance, just make sure this statement is clearly written somewhere on one of your note sheets, one of your 2 note sheets. Okay? All right, so we spend quite a bit of time on Lewis structures, and I don't think I need to worry about part D of problem 3, because that's essentially what I was trying to ask. When the hydrogen comes in, right? Okay, which oxygen is it going to be bonded to? Okay, the answer is it doesn't matter. These 2 oxygens should be identical. Okay, there's no resonance structure here. Okay, I mean, I take your comment earlier saying that, you know, if there's only single bond, then there's no resonance. If there is a double bond, it doesn't automatically give you a resonance. You still have to check, okay, to see if this sort of ideas apply to your situation. Like if I have C2H4, this one does not have resonance. Okay, because you might think, well, okay, I can just switch this single bond here with this double bond here. So put the double bond over here. Is this the resonance? No, because hydrogen cannot form double bonds. Okay, hydrogen cannot form double bonds. So there's no other way for you to put the double bond in C2H4 except to be, you know, except right here in the middle between the 2 carbons. So there's no resonance for C2H4. Okay, so you have to be really, really careful here as far as identifying resonance structures. And hopefully with experience and, you know, with more time, you'll be able to do this more successfully. I'm sure at the beginning of the year that you begin taking organic chemistry, you'll be given a lot more exercises that would test your ability to identify resonance. Okay, so now let's quickly look at 4, because 4 is actually very much related to 3. So let's look at problem 4 on the practice exam. Because 4 is basically what? Part A asks you for a formula for magnesium nitrate. And I'm sure you can write it by now. In fact, I'm not going to ask you a question on this. Okay? You know, to write a formula for a compound between magnesium and nitrate. I mean, I asked you this already on the first exam. And maybe I'll ask you on the final, something like this, but not on this exam. And then part B asks you to write a chemical equation for the dissociation of MgNO3. So, you know, basically the answer key tells you that this is supposed to be the equation that you should write. Okay, so I'm just giving you directly the answer. Okay, so, I mean, it's a matter of how you represent magnesium nitrate when it dissolves in water. Okay?
How come that couldn't be a double replacement reaction?
It's not a double replacement, it's just dissociation. Yeah, it's just dissociation. There's not a single, I mean, there's not a second reactant. There's only one reactant. Apparently what happens is, you know, this guy just breaks into 3 pieces. Okay? So if you can imagine, right, I didn't bring the model, but, you know, just pretend that this is magnesium, okay? And then you have nitrate. So I don't know, just put the N on the nitrate. Then you have another magnesium, you have another nitrate. And then, you know, this pattern kind of, you know, continue, right? So I know I'm not doing it right because, you know, it's twice the number of nitrate per magnesium. So somehow this structure is not necessarily representing what really is going on. But let's see if I can, you know, just, I don't know, try to give you an idea. But, you know, magnesium nitrate, if you buy it as a solid, it's like sodium chloride, just salt. Okay, you're going to see crystals, you know, little cubes of magnesium nitrate, or powder. You know, I might not have the right description here, you might see powdery magnesium nitrate or crystalline magnesium nitrate. But fundamentally, the solid form of magnesium nitrate is like this. It's like a crystal lattice. So you would have a certain lattice energy associated with it. So it's just a crystal lattice. Okay, so when you dissolve magnesium nitrate in water, okay, water molecules, H2O, just basically pull the magnesium and nitrate apart. Okay, so instead of having one giant crystal, you're going to have separately the magnesium ions. So all these bonds are actually being broken. All these ionic bonds are being broken. Why? Because now you have a bunch of water molecules that are capable of surrounding each of these ions. Okay, whether it is positive or negative. So you have to imagine that these water molecules are very powerful. They can just pull in a magnesium ion and surround it. Okay, so that magnesium stays dissolved. Okay, and that's what's represented here. Magnesium being dissolved, and the nitrates, the two nitrates, are also being dissolved in water. So that's what that is. Part B. Okay, which again I'm not particularly concerned about this on this upcoming exam. And then part C basically asks you to look at nitrates and use VSEPR theory to predict the shape. But since I already told you that I'm not going to ask you to predict the shape or predict the shapes of molecules, so I'm just going to probably, tell you that the shape of the nitrate ion is trigonoplanar, and I just want you to give me some idea, okay? How can you use VSEPR theory to predict the shape of anything, including that of the nitrate ion, NO3 minus? And then I guess part D, once again, ask you to look at the resonance structures of nitrate. And I know that we have spoken about that already, so I'm not going to elaborate too much on that. But if you want to take a look at my answer key, then it would have some more details, a little bit more than I guess what I'm writing on the whiteboard. Now, problem 5. I guess that's what you're asking me about. Problem 5. So we've gone through 3, we've gone through 4, and now we're on 5. Okay, now we're on 5. And 5A, okay, well actually A, B, C, D, and E, they are all independent questions. Okay, and so these are just basically short statements that I ask you to provide explanations for. So problem 5, part A, asks you to explain this. There are more lone pairs on the central atom in XeF4 than in SF4. So you're comparing two molecules, XeF4 versus SF4. Okay? So you have to explain how come this one has more lone pair on the xenon than on sulfur over here. So you have more lone pair on xenon than on sulfur. So that's basically what I asked you to explain. And since you're not expected to draw structures, I'm going to actually provide the structures to you. So here's Xe, here's S, and here you have F4. So we've got 1, 2, 3, 4. 4 fluorine. And SF4 is kind of very similar. It has 1, 2, 3, 4 fluorines. Okay? Now the problem is fluorine has 7 valence electrons. Okay, I mean I wrote 7 electrons, but here I am only referring to the valence electrons of fluorine. Okay, so fluorine, each one has 7 valence electrons. And if you remember the octet rule says that 7 is not a good situation, but 8 is good. So all fluorine wants to do, each of these fluorines wants to do, is to share 1 electron with xenon. Okay, so fluorine has 7, right? 1, 2, 3, 4, 5, 6, 7. Those are the 7 electrons. So all fluorine wants from xenon is just 1 electron, 1 more electron, so that they could share. Okay, so the fluorine can share with xenon. And so this becomes a single bond. And it's the same situation here, 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 here. Okay, so that's why you have all these single bonds. Now the problem with xenon is that xenon has already 8 valence electrons. Okay, if you look up xenon on the periodic table, xenon is actually one of the noble gases. So it has already 8. Okay, so why does xenon wants to form a bond with fluorine? I don't know. I mean, honestly, I don't know why xenon wants to form a bond with fluorine in this case. Because xenon by itself is already stable. Xenon has 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. There's no, there's no motivation for xenon to form any bond. That's true for all the noble gases, right? Okay, you know that? There's no motivation for noble gas to form any bond. But, we actually found this compound somewhere. So we have to talk about it as far as bonding. So fluorine is going to form single bond with xenon. Okay? So in other words, 4 of the 8 electrons from xenon. It doesn't matter which 4. So 1, 2, 3, 4. 4 of the xenon electrons, okay, will be kind of shared by the 4 fluorine atoms. Okay, leaving behind what? 1, 2, 3, 4. There are 4 more electrons that will just be stuck on the xenon. And what are we going to call these? Lone pairs. That's right. These are lone pairs. Okay? So xenon tetrafluoride has 2 lone pairs. But what about the case of sulfur? Okay, well, sulfur has how many valence electrons? 6. Yeah, that's correct. Okay? Sulfur has 6 valence electrons. Okay, so 1, 2, 3, 4, 5, 6. Put them any way you want. But likewise, it's SF4, so 4 of these 6 electrons are already being used to form the 4 single bonds. So how many electrons are left? Only 2, so the 2 are stuck on the sulfur. So you got 1 lone pair. So which molecule has more lone pairs? Yeah, that's the one on the left, right? Xenon, tetrafluoride. So that's how you're going to explain it. Okay, one has 2 lone pairs, the other one has only 1. Okay, but in both cases, you might as well just mention how come xenon and sulfur, they're both stable. Right? So we call this, say again?
You said both what?
Well, both of these situations are stable.
Stable.
So what do we call this? In chemistry terms, this is called expanding. What? Expanding. See, we come up with names for everything. Resonance stand for this. Yeah, expanding the octet, that's right. This is called expanding the octet. So if someone asks you, okay, what's going on here? How comes you have 10 electrons on xenon? Actually, you have 12. 12 electrons on xenon and 10 on sulfur. Okay? Well, you don't have to say much. Just say, that's the way it is. It's called expanding the octet. Okay? So beyond 8, that's expanding the octet. But you know, not every element can expand octet. Can calcium expand octet? No. Okay. Can helium expand octet? No. Okay. Only very few elements can do this. Like I mentioned those already in class. Like phosphorus can, sulfur, chlorine, bromine, maybe xenon and argon. That's about it. Okay, only very few elements can actually expand the octet. These are the ones that are typically being mentioned.
I have a question.
Yeah, go ahead.
Does helium, is it considered part of the octet?
Well, helium kind of follows the plan of hydrogen. Okay, because hydrogen and helium are too small. So I mean, if you put 8 electrons on helium, that's too many, right? Because helium has only 2 protons, hydrogen has only 1. So you know, if you surround hydrogen by 8 electrons, you know, 1 proton is not going to be able to handle 8 electrons. Okay, so that's not a good situation for hydrogen. Same for helium, you know, got only 2 protons. So if you put 8 electrons around helium, that's too many. So hydrogen and helium does not follow the octet group, but they follow what is called the duet group. It's not a very big name here, but it's basically saying, okay, well, helium has 2 valence electrons, then helium is stable. If hydrogen, which has 1 electron, can acquire another one somehow, then hydrogen is also stable. So instead of the octet, then the duet. Does that answer your question? Now, if you look at 5b, okay, we just push on to 5b. Okay, it says MgO has higher lattice energy than KCl, and we have to provide an explanation. So now we are looking at 5, and this is part B. So MgO has higher lattice energy than KCl. So why does magnesium oxide having higher lattice energy than KCl?
Does it have to do with the difference in electronegativity between oxygen and chlorine?
No, unfortunately. In this case, it's not electronegativity. Because electronegativity will only tell us that this one is ionic. So is this. Okay, that's the only thing that electronegativity is going to tell you, is that MgO is ionic compound. So is KCl. That's it. There's nothing more you can tell from electronegativity. So the only way that we can kind of look at this idea of lattice energy is to look at the specific ionic bond. We'll compare this ionic bond to this ionic bond here and see which one is stronger. Okay? And you know, this might be difficult if you don't know the charges on the ions. So let's put the charges on the ion. Okay? And hopefully that will give you a pretty clear picture. So Mg and O, the charges are 2 plus and 2 minus. KCl, there's a +1 on K and a -1 on Cl. So why is this one more difficult to break? This bond than this bond right here. Why? Anyone wants to?
Is there a higher
Sure,
bond
yes.
energy between magnesium and oxygen and potassium and...
Yeah, that's
chlorine?
given. That's why the lattice energy is higher here than here. Okay, you said the charges. What about the charges?
They're higher.
Yeah, just higher. Yeah, this is a +2, -2. Over here, it's just +1, -1. Okay. Now I don't know how much you know about physics. Okay, but these charges multiply when you determine the force. Okay, force is basically the charge multiplied divided by the distance of separation. So let's assume these are all very small, and so they're being separated by approximately the same distance. But the force depends on the product of the charges. So you have 2 times 2, actually 2 times 2, which is 4. And here you have 1 times 1, which is still 1. Okay, so 4 is a lot bigger than 1. Okay, so that's why the force is here. Or versus something like, I don't know, aluminum oxide. So you have Al3 plus and O2 minus. Okay, so if you compare aluminum oxide versus magnesium oxide, which one has a stronger bond?
Aluminum
Yes,
oxide.
aluminum, yeah, that's right. That's why I created this example to show you. The aluminum oxide is going to have a stronger lattice energy. It's going to require more energy to break the ionic bond. So here, don't mention electronegativity, because it has nothing to do with the strength of the bond. Electronegativity is only going to inform you the only fact that we know already about these compounds. They're both ionic compounds. Okay? Why? Because magnesium has low electronegativity. Okay? Potassium has about the same electronegativity, which is low. Oxygen has high electronegativity. Chlorine has also high electronegativity. And they average to be about medium. Okay, so there are large differences, and the average is about medium. So this is characteristics of ionic compounds. So they both fit in this description, and therefore they're both ionic. But beyond that, there's nothing else you can use electronegativity for. Okay, so be very careful here. Okay, so part C, if we can just go through this one until the end. Part C said metals have properties of being ductile and malleable. So metals are both ductile and malleable. Okay, and there's not much to it. I mean, not much more to it except some basic observations being given for metals. So, okay, so how do you explain metals being ductile and malleable? This just means that you can pull into a wire, something like that. You can just pull a piece of metal until you form like a wire. Okay? This means you can hammer the metal into a thin sheet. Okay, so you can pull on the metal and make a wire. Or you can hammer on a piece of metal into a thin sheet. But I guess the key to this here is that, okay, so let's say you start off with copper. You start off with like a block of copper, a cube, a pretty, pretty reasonable sized cube of copper. Well, you can hammer it into a sheet of copper, or you can, somehow pull it into a wire. But, at the end of this, whether you have a wire or a sheet, it's still copper. Okay, you can still, kind of pass electricity through the piece of copper. Okay, so before and after does not make a difference. So it's, to us, I mean, at least to the chemists, this is very interesting. We thought that when you do this kind of thing to a piece of copper and hammer it, then it would lose the property of being copper. But, the resulting evidence is very striking because the thin sheet is still pretty much the same as, it still has the same properties as before. Okay, so what is the explanation to this? So we come up with this idea, which is called metallic bonding. Okay, and basically here's the idea, right? You have these, copper atoms that are kind of bonded together like this by metallic bond, which is unlike ionic and covalent, or ionic or covalent. It's a very different model, right? Because it's not sharing electrons, and it's not, the positive, negative ions attracting, like in this case, or this case. So this just, the copper metals, okay, the atoms of copper metal, basically, being packed together, okay, and their valence electrons are mobile, and they are being essentially, left gathering on the surface of a piece of metal. So imagine, right, if you actually hammer this piece of metal. So, to make, instead of 3 layers, now you have only 1 layer of atoms. Okay, so you hammer it so that you are essentially changing the, the position of the atoms with respect to each other. Now, does that change the way the atoms are bonded together? No, right? Even though you hammer the atoms so that they are all now out of position, but the metallic bonding part of this metal is still pretty much maintained. Okay, which is very interesting because you cannot do this to ionic compounds. When you hammer an ionic compound, it's totally, broken apart with all the positive, negative ions. I mean, imagine, right? Any sort of misalignment is disastrous for an ionic compound, right? Imagine this situation being put together. These positive ions will repel each other. These negative ions. I mean, if you just shift the ions by a little bit, okay? Put the 2 positive ions next to each other, put the 2 negative ions next to each other. It's disastrous. Right? This whole thing might just kind of, fall apart because, that's how strong these interactions are between ions of like charges. But for metallic bonding, no problem. You can, kind of put the atoms any way you want, and still, the piece of metal continue to carry properties of being metal. So that explains both. Okay, just metallic bonding explain why metals can be pulled into wires as well as being hammered into thin sheets. Okay, and then part B is actually very similar. Part B just actually explains why metals are good conductors. And obviously, with so many electrons that are mobile, these are mobile electrons. I mean, in the case of the covalent bond, like here, these electrons are pretty much trapped in the bond. I mean, these are electrons shared, so we tend to think of them as being localized. Okay, unlike these electrons here that are delocalized. I know you don't like new terms, right? But the book is full of them, and that's how scientists talk to each other, chemists talk to each other, using these very special terms. So the electrons here are delocalized, whereas the covalent bonds have localized electrons. So here the delocalized electrons are mobile, and therefore if you keep pushing in more electrons, some of these can actually leave. Okay? And why does that matter? Because that's how you keep a current flowing. Right? Current is basically a flow of electrons. So if you can keep the electron moving, that something is going to conduct electricity pretty well. So that's how you would explain it. And I'm not going to worry about part E because I mentioned about the packing efficiency. Okay, and we never really talked about packing, so you can kind of ignore that. The only thing else on the practice exam I would like to bring your attention to, because I think number one you can answer pretty well. We spend a lot of time talking about periodic trends and valence electrons and chemical properties. So number one is almost like a given. You're guaranteed to be asked some of these questions on the exam on Monday. And so you might as well just gather yourself together to be ready to answer a few questions on the periodic trend. And then number 2, I think we went over it last Friday in the tutorial. Okay, and I did some examples in class, so I hope you'll be able to just look at the combination of any 2 elements and be able to say something, be prepared to say something about the way that they're going to bond together, whether it's going to be primarily ionic, covalent, or metallic bonds. So the only question that I would like to just take an additional couple of minutes to go over with you is problem 6. And it's not a very difficult question. If you just put your mind together for one more little piece of knowledge. Okay, so problem number 6 on the practice test. Okay, it's basically describing a chemical reaction that looks something like this. Okay, so I'm going to jump to part C. So this is problem 6, part C. It says the hydroxyl radical, which looks something like this. We just call it hydroxyl radical. Like to react with CH4. Okay, in order to form the methyl radical, CH3 with a dot, and water. Okay, so you're given these reactants and products. Okay, what you're being asked to do is to calculate the delta H of reaction. Okay, so you need to calculate a value for this. So you ask, well, what is delta H of reaction? Okay, well, this is something I kind of hope that you learned before the first exam. So if you just put energy on one axis, and if you put reaction direction or reaction coordinate on the other one, okay, then there are 2, kind of situations you can look at. Right, you have 2 graphs, okay, 2 identical axes, but 2 different situations. One is your reactant energy is lower than the product. The other is you have reactant energy higher than product. So what does this represent? What does this situation present to you?
Endothermic reaction.
Exactly. Okay, we just call this the delta H of reaction. Okay, but it just clearly indicates the case of an endothermic reaction. That's about it. And we know every chemical reaction is going to be either endo or exothermic anyways. Okay? Because rarely do you have the reactant and product on the same energy level. I mean, just very rare. I mean, look at these bonds. Okay? When you form a chemical reaction, some bonds are going to be broken. Some new bonds are going to be formed. Okay? How often do you have the same energy? Right? It costs you the same amount of energy as the energy that will be released because of the formation of the new bonds. Does breaking bonds require energy?
Yes, it does.
Okay. Yep. So, and then you go over here, forming bonds release energy. Okay. So this is energy released, energy required. How often do you have, the same number on both sides? That the energy released is the same as the energy required. Okay, rarely are those 2 going to be the same. So it's bound to happen, right? Okay, it's either the product, does not release as much energy as the energy required to break all the reactant bonds. Well, in that case, you have an endothermic reaction. But otherwise, you would have isothermic. Okay? So the way that we can determine is we calculate delta H and use the sign and magnitude of delta H to help us answer this question. Okay, so both the number, the magnitude, as well as the sign are both important. So endothermic reaction, delta H is going to be positive. Okay, isothermic reaction, delta H is going to be negative. So I hope that you remember this from the first exam, and if not, then learn it down, because it will be important on the final. So the class that I missed that Wednesday when Dr. G came and substituted for me, he explained, hopefully, how to do this kind of calculation. Okay? So basically, you're looking at a chemical reaction and you're thinking, okay, I need to break all these bonds in the reactant molecules. And I'm going to form all these new bonds in the product molecules. Okay, so bond breaking requires energy. So all these bonds require positive energy. Okay, while going over here, you're going to form these new bonds. Right? Every time you have two atoms that are bonded together, some energy will be released, because initially you have two atoms that are apart, but now they're bonded together, so they move as a unit. And then some stability is implied, obviously, and therefore the additional energy or the excess energy has to be released, right, in order to keep the conservation of energy alive. That whole principle. So the idea is, okay, so you're being asked to calculate delta H. So I'm going to keep track of delta H by knowing exactly how much energy are we talking about here, and how much energy are we talking about here, and we're going to add the two together. Okay, so let's go in and look here. In the first reactor, okay, what kind of bond must be broken?
Oxygen,
Yeah,
hydrogen
it's
bond.
the OH bond, right? So you look up the energy of OH bond, and let me do it really, really quickly. Okay, the OH bond energy is 460 kilojoules per mole. Okay? Here, we have to break some CH bonds, right? So, and for every CH bond, it's going to be 414 kilojoules per mole. But guess how many CH bonds we're breaking? 4. Yeah. Okay. In fact, we need to check to make sure the equation is balanced. But here, I think it is already. But what I would do is, I'm just going to break one OH bond, cost me 460 kilojoules of energy, and I'm also going to break 4 CH bonds, which is going to cost me 4 times 414 kilojoules per mole of energy. Okay, so all these will be positive. These are all energy required. Now what about getting back some energy by having some new bonds form? I'm going to get back 414 kilojoules per mole times 3. Right? I'm actually going to get negative of this energy because of the formation of the 3 CH bonds. And let's see, how many OH bonds are to be formed in the reaction?
2.
Okay, each one is 460 right, kilojoules per mole. So I'm going to have 460 times 2. So if you do all the math, okay, you add 460 to 4 times 414. So let me write it over here. So it's 460 plus 4 times 414. Okay, and then minus, well, it's actually adding, but you're adding to a bunch of minuses, so it becomes minus. So it's minus 4 times 414 minus 2 times 460. Okay, so once you set this up, it becomes just elementary school mathematics, right? Because you're just adding and subtracting, multiplying. So hopefully you end up with this answer, minus 46 kilojoules per mole. Okay, so I said before both the sign and the magnitude are important. Now the magnitude tells you that was 46 kilojoules per mole. Okay, is that a whole lot of energy? 46? Okay, well, is it enough to break a typical single bond, which is like 200 kilojoules per mole? 46, is it bigger than 200 or less than 200?
Much.
Yeah, much less than 200. So it's not a whole lot of energy we're talking about here. Okay? Because when this number becomes more like 200, 400 kilojoules, then it becomes significant. So 46 is not a big number. And in addition, it's negative 46. Okay, so the negative is important because it's telling us that this reaction is exothermic. Well, not a whole lot of energy is being released, but at least it is exothermic. I mean, unlike the combustion of fossil fuels, right? If you burn octane, which is the way that you obtain energy to run a car, okay, that kind of reaction, just burning gasoline, okay, would be exothermic, and this number would be enormous. Okay, would be minus a huge number of kilojoules per mole, because that's primarily why you want to burn gasoline. It's not to create CO2, which is actually an environmental problem. But remember, you have gasoline, and then you burn it in your car engine. Okay, well, you're not interested in the CO2 and H2O being generated, right? You're only wanting the heat, this amount of energy that you actually got from this reaction, so that you can use it to drive your engine. But at the same time, you generate CO2 and H2O, and these are eventually going to end up in the atmosphere, and you know already, because we talked about this in class, that this is a greenhouse gas. So this kind of contributes to global warming, depending on whether you buy into the idea or not. But nevertheless, okay, so these sort of endo and exothermic reactions are pretty important. Okay, so and we can kind of get an idea by looking at these specific bonds being broken and specific bonds being formed, which is a pretty nice idea, right? Because otherwise, you look at this reaction and you have no idea why this is an exothermic reaction. But now you have an idea, because you can compare the bonds and figure out, okay, we actually get back more stability in the product molecules than when compared with the energy of the reactant molecules. So that's why the product molecules are more stable than the reactant molecules. So all the excess energy got released into the atmosphere. So it's the reason why it's minus 46 kilojoules per mole when it comes to the delta H calculation. So again, so this exam, I think the key is, between those of you who are prepared and those of you who are just walking in code, because if you walk into this exam, having only a few things written down on your note sheet, then you're probably not going to do very well, because I don't expect you to remember the whole book. So it's a matter of, okay, actually getting some preparatory work done and bringing 2 very good note sheets.
So any question where we need like the electronegativity or the ionization energy, will you provide that information?
I will provide all those.
Okay.
Yes, all these electronegativity, ionization energies, atomic size. If you need that for to answer some questions, then I'll provide those numbers to you. Okay, these bond energies I'll provide to you, so you don't have to worry about having to memorize or bring in any data sheets. Okay, but going back to what I was saying, okay, so the difference between those of you who are going to be doing well in this exam and those of you who are just getting below average, it's going to be your preparation. So I strongly urge you to, find yourself a little time, sit down in a quiet place, and start putting together some note sheets, okay, for your own use during the exam. Otherwise, if you walk in without anything, it's very likely that you're not going to be able to do very well. Okay, so good luck, and yeah, more questions. Oh yes, the attendance sheet is over here. So I just put 4/13. That's today's date. So you can just indicate, your attendance. That would be fantastic.
Professor, what time?